Right, Assalamualaikum warahmatullahi wabarakatuh and a very good morning. Right, so today we will continue our lesson. We will cover chapter 8, which is Amperes Law. The topic that we will cover is first the Amperes Law, second the magnetic flux and the flux density, third the Cole and Stokes theorems. Okay, for our previous lessons, we already covered the Biot Savart law. Actually, the Biot Savart law is almost similar with the Coulomb's law, except we are deal with the cross product. The cross product means that the direction of your current and R is always perpendicular with the direction of your field. Right? So you actually can determine the direction of magnetic field intensity by using your right hand grip rule. Alright? So basically your thumb will be your direction of current and your other finger is the direction of your field, right? For this is just a history. The Amperes law is discovered by Andrew Marie Amperes in 80s. So it's quite similar with the Gauss law, right? Hopefully you still remember what is the Gauss law all about for electrostatic, right? When we have a special case of charge distribution, for example, we have symmetrical charge like a spherical charge, or we have an infinite surface charge, or we have a very long coaxial, and so on. We can use the Gauss law to find the electric field intensity because the field is symmetrical. Right. So for the Amperes law, so basically this is a special case of current distribution. It's quite similar. So for the special current distribution, we can use a magnetic field. You can find the magnetic field by using Ampere's second law, right? So what is the special case of current? So it's almost similar. The current should be symmetrical and it should be infinite, right? So we will see later how it is mean. Alright, the Amperes second law states that the line integral of the magnetic field intensity H around the closed path is the same as the net current I enclosed by the path. So when we create a path, right, so basically this is what we call the Ampere loop, right? So what is the current enclosed by this loop? So we only considered the current inside the loop. If there is another current outside the loop, so we will not consider. This is the same with the Gauss law, right? Okay, for example, we have the first case, we have the H because we have a current. Second case also, the Ampere loop, we have a current, but the third case, the current is outside our Ampere loop, so the H will be 0. Another example, let's say we have a 5 current source and we create the Ampere loop here, then only cover the 4th current source, right? So this is basically the current going out from the surface. This is the current going in. So we only consider the 4 current here, and the 5th current we will ignore because the current is outside the Ampere loop. So what is the Ampere second law state? Okay, this is the formula. The closed integration of H dot dl is equal to I enclosed. Alright, the H dot dl is basically the line integration of the H through the dl. So this is our dl, okay, the Ampere loop. So you can see here that the H is basically parallel with our dl because this is a dot product. So that means our H is also in the same direction with our dl. And the I enclosed is what? the current source enclosed by the Amperean loop. So for example, in this case, we have a 4 current source that enclosed by the Amperean loop. So this 4 current source will contribute to the H. But another current source I, which is outside the Amperean loop, will not contribute to the H. And our I enclosed can be the line current or filament currents, okay, which is the current flowing through a very thin wire, which is the cross surface, the cross section area can be neglected. And then we have a JSDL. The JS is basically the surface current. The surface current is like we have a multiple line current which is arranged in parallel and pass through a certain DL. Okay, this is for the thin sheet lah. And then we have the volume current, the J dot the DS. Okay, both are vectors. Okay, it has the same basically it is parallel lah. The J is parallel with the DS. So the J here, we have the volume current. For example, I have the cylinder material where the DS is the DS is significant, right? So the volume current will flow in pass through the DS. Okay, so the J dot DS is basically actually the current. So I equal to JSDL equal to JDS is a current where the unit is ampere. The same thing, only how the condition of the current exists. So as a comparison and conclusions, let's see what is the similarity between the Gauss law and Ampere circuit law. For the Gauss law, we know that we analyze the infinite length of line charge or infinite surface charge, or we can analyze the symmetrical charge like sphere charge. For Ampere circuit law, we analyze the infinite length of filament current, infinite surface current, or we have infinite volume currents. But in the case of the finite length or finite surface, we cannot use the Ampere circuit law. We need to use the Biot Savart law. For the Gauss law, we create the Gaussian surface, okay, to find what is the D. So the D pass through the DS, okay, is equal to the Q enclosed. Okay, the Q enclosed. And here for Amperean loop, okay, basically we do the integration of H dot dl, the Amperean loop equal to I enclosed. So this is the surface integration, this is the line integrations. So this is I equal to JSDL, the line integration, and J dot ds, this is a surface integration, where I enclosed is a total current inside the closed loop.